Okay, so let's look at this third example on solving by matrices. Again, we have a system of 3 equations and 3 unknowns. We have to make sure that the equations are set up correctly. Are they? Good, which means we can set up a matrix, what's the order of this matrix? Good, another 3 by 4. So let's get that established. By the way, if they ever not write a variable, like it says x plus y equals 3, that means the z equals 0. Agreed? Okay, just making sure that we know that. So if they ever leave one of these variables out, you're like, hey, every other equation's got 3 variables and this one has 2. Well, put a 0 in and that'll make your third variable, right? Okay, so we've written our matrix. What do we do next? Yes, we identify the main diagonal. Then what do? Good, we eliminate the x's, correct? So what's the first one we got to get rid of? Good, this -1 by using the other -1. So one of those has to be positive, right? Does it matter which one? Nope, so I'm going to take -1 and multiply it by the first row, add it to the second row, and the answer goes in the second row position. Excellent. So when I start writing this particular matrix down, I'm going to write row 1 because I'm not trying to get a 0 in row 1. And then for row 2, I clearly have some work to do. So I have to multiply the first row by a -1, which will make it a +1, -1, -1, and +3. Add it to the second row, and the second row is a -1, +4, -17, and -24, and add them together, and this is what I ended up with. Okay, so, got it. But we still need to make that 7 into a 0, so how are you going to do it? Yes, you still have to use that -1 on the main diagonal. Remember, it's an x, and you're not going to get rid of it. So it looks like we have to take 7 and multiply it by the first row, and add it to the third row, and my answer will go in the third row position, won't it? Okay, so let's take a look. So we said we have to do 7 times the first row. What will that give me? Yeah, -7, 7, 7, and -21. And the third row is a +7, -4, -25, and yeah, that's 0. Add them together, and it looks like that's what I get. Hopefully we're in agreement. Okay. And now we have just done what? Whoops. I'm sorry, I wrote the wrong number here. See, this is why I need you guys doing the work with me. This is a -21. I know some of you caught that. Okay, so what did we just do from the original matrix to this matrix? Yes, we eliminated x's. I heard you. So, eliminated x. And then what did we have to do? Yes, we have to eliminate the y's, but what do we try to do in between? Good, we try to see if we can do any reducing, right? And I'm noticing I can reduce rows 2 and 3. I can reduce row 2 by 3, and I can reduce row 3 by 3 also. So, I'm noticing the first row isn't going to change. Do you agree? And the second row, we said we can reduce it by 3. Remember, the only reason we're reducing is just to make the numbers more manageable to deal with. That's all. I just want to make them more manageable to deal with. I'd rather deal with these numbers than an 18 and a 21. Does that make sense? Okay. Now that we're reduced, what do we have to do next? Good, get rid of the y's. So stay tuned. I'll be right back to help us get rid of the y's. Okay, so we got rid of the x's. We reduced. Now it's time to get rid of the y's. So what do we do first? Good, identify your main diagonal. And now I'm trying to get all the numbers above and below it to be a 0, correct? So this 1 has to go first, so we're getting rid of our y's. And I'm using the 1 on the main diagonal, because I'm not trying to make it a 0. And it is a y value, and I can only use y's to get rid of other y's, right? Okay, so, and it doesn't matter which row you multiply by the -1, agreed? So, I am going to multiply, well, let's just do row 1 times a -1. How's that? We'll add it to row 2, and the answer will go in the row 1 position. So, I know I'm going to have some side work that I'm going to have to get done here. So, down here, we are going to do -1 times the first row, which would be +1, -1, -1, and +3. Add it to the second row. So that's a 0, 1, -6, and -7, which gives us 1, 0, -7, and -4. Okay, got it. And now we need to get this 1 in the third row for the y's, also a 0. And I'm going to use this 1 on the main diagonal. So again, it doesn't matter. I think I'll multiply the -1 by row 2, add it to row 3, and the answer will go in row 3, won't it? But wait a minute. I haven't written row 2 yet. Is row 2 going to change? No, because I'm not trying to get a 0 in row 2. Because the number, this 1, is on the main diagonal, so I'm not trying to get a 0 there. So we leave that row alone. Okay, now let's work on the row 3. So I'm going to do -1 times row 2, which will give me 0, -1, +6, and +7. I'm going to add it to row 3, which is 0, 1, -6, and -7. And when I add, well now, isn't this interesting? I have an entire row that went to 0. You're like, now what do you do? Well, now let's think about this, okay? This entire row went to 0. It wiped out all my variables, agreed? So, remember something. This dotted line means equals. So in row 3, the left side is nothing but 0, and the right side is a 0. So answer me this. Does 0 equal 0? Is that a true statement? Yes, it is. Because one of my rows went to 0, and I have a true statement because 0 does equal 0. This means I actually have a dependent system, which means in this particular case it could be two equations that are the exact same equations. Could have been all 3, but we're just going to say 2 equations that were the exact same equations. So if I actually go to graph them in the 3-dimensional world, they'll be the exact same line. So you're like, well, so what's the solution? Remember, the solution for these dependent systems is an infinite number of solutions. And my solutions are still made up of x, y, and z. Are you with me? They're still made up of x, y, and z. So let me show you on a dependent system like this how you're going to find your x, your y, and your z. I'd like you to notice the first 2 equations, or the first 2 rows. Those are still actually 2 equations, aren't they? Because that third row went to 0, there's no more work for me to do inside the matrix. So what I'm going to do now is I'm going to translate the last 2 equations I have left, which is out of rows 1 and 2, and I'm going to translate them back into an actual equation. So that first row basically says x minus 7z equals -4, correct? And the row 2 equation looks like y minus 6z equals -7. Agreed? Okay. Do you notice in both of these equations, the one variable that's in common is the z? So this is an interesting phrase. So hear what I'm saying. I can write x in terms of z. I can write the y in terms of z. Now, when I say it that way, you're like, well, what does that mean? If I'm writing x in terms of z, that means I'm solving for x. If I'm writing y in terms of z, that means I'm solving for y. So watch. When I solve for x, I'm going to add over the 7z. Now, x is in terms of z, which means x is isolated, and the variable on the other side of the equal to sign is z. X in terms of z. On the second equation over here, when I solve for y, I'm going to get y in terms of z. I isolated the y, and the variable on the other side is z. With me? Okay. Now, we know that our solution is supposed to be x comma y comma z, the order triple. Well, I know what x is. X isn't a single number. X is actually this little equation. So I'm going to write 7z minus 4 in place of the x. And instead of writing y, I'm going to say 6z minus 7. And I don't know what z is, so we leave z as z. So here's the deal. I have an order triple, all in terms of z. The x is in terms of z, the y is in terms of z, and clearly the z is in terms of z. This is a dependent system, because whatever number I choose for z, x and y will be dependent on that number I choose for z. This is why I have an infinite number of solutions, because I can choose any number I want for z. I can choose positive 5, negative 100, 1/3, negative 2 and 7/8, whatever. Are you with me? Okay. Now, let me show you a what if. Back up here where we got 0 equals 0 basically, here's a what if. On this side of the equal to sign, what if this number had been, oh, I don't know, let's just say that number had been a 2. If that number had been a 2, then this line would have translated to 0 equals 2. Remember, this is a what if part, right? I'm posing a what if problem. I would have had 0 equal 2. Is 0 equal 2 a true statement? No, this is false, which means this is your no solution system. This would have been the inconsistent system. So, if all the variables wipe out and you're left with a true statement, you've got a dependent system. But if all your variables wipe out and you're left with a false statement, then you've got a no solution system, and it's also known as inconsistent. Good? Okay, so hopefully this made some sense to you. Hopefully you're getting the hang of it. You have fun with matrices, and I'll catch you on the flip side.